Hello guys, I'll be doing a video on integral identities. I chose to do this first, before doing anything on differential identities, because I'll be spending more time doing differential equation videos, and I think this is useful for that, especially for those taking differential equation classes. It took me a while, and it was hard deciding what to cover because it's a lot. I would try and spend more time on this and show you guys how you use U-substitution coupled with the first integral identities I have here to solve a lot of questions. It's so powerful when you are able to combine U-substitution and this. And I'll try and venture into integration by part, which is this, and then I would try and cover some trig integral identities, hopefully within this video. I take that this is not going to be the only video I'll do on integral identities, because really it is a lot, and I'm trying to make the video not too long and focus on the key aspect of integration. So I hope you enjoyed this video. So I would start with a little bit of differential calculus, just to introduce the first identity I have here. So I'm sure most of us know this. When you have a function y is equal to x to the n, and you are asked to find the derivative of this, you simply derivative with respect to what's it called, x, you will have d dx of x to the n. And what do? The exponent drops down, and then the exponent is updated by reducing it by 1, right? So you have nx n minus 1. That's what we do for a polynomial. This is a polynomial of a single term. If you have your y defined as this, if you have your y defined as this, y is equal to x to the n plus 1, same thing, if you're going to take the derivative of this, the exponent drops down, right? N plus 1, right? And then the exponent is updated by subtracting 1. So what you will end up with is n plus 1 x to the n, right? So the derivative of this gives you this. And what do you understand by integration? The integral of a function is just the antiderivative, it's just the reverse. So what this means in essence is that if I have n plus 1 x to the n, sorry, let me write this part. If you have the derivative of x n plus 1 is equal to n plus 1 x to the n, then by integrating both sides, you will get the antiderivative. So what it means is, if I integrate this side and I integrate this side, integration is the inverse or the reverse of derivative. So this cancels this, so you have x n plus 1 is equal to integral n plus 1 x to the n. And maybe I should have covered some basics of integration. If you have the integral of a function times some constant, say you have this, you can rewrite it as what? K integral f of x, right? what it means is that integration is associative when you have a constant multiplying your function. The constant can be factorized out of the integration, and then you just find the integral of the function itself. What that means is that this can drop out, and we have xn plus 1 is equal to n plus 1 integral of xn. So I can divide both sides by n plus 1. N plus 1. So the integral of x to the n, so therefore the integral of x to the n is equal to xn plus 1 divided by n plus 1. And that's what we have here. Yeah. So that's how this derivative came about, this integral came about. We know that when we take the derivative of the function, the exponent drops and the exponent is updated by subtracting 1. So when you take the reverse, which is the integral, you add 1 and then divide. So you drop exponent and update it by subtracting 1. So you have to start from here. You update it to, so this is differentiation, and when you integrate, you start with what? Updating it by adding 1 and divide. Divide. So you just do the reverse, and that's what it is. So this just to show that this is indeed going to give you x to the n plus 1 over n plus 1. Now, just to add to this, we always do integration of polynomial term by term. You don't do it as a whole. What I mean is, if you have integral of function 1 of x plus function, or plus minus, it doesn't matter, function 2 of x plus function 3 of x plus function plus whatever function n of x dx, and this is, I stand corrected, it could be polynomials, it could be other functions. It doesn't have to be only polynomials. If you add in several functions together and you're trying to evaluate the adding or subtracting, and you're trying to evaluate the integral, you can, how we do it is to have the individual integration done, right? Plus minus integral f2 of x dx plus minus, continuing to the last one, fn to the x dx plus minus. So you break it down and do them term by term. Same thing for polynomials, that's what you do. And that's what makes, so in essence, integration is distributive, I believe. Distributive is the word, over addition and subtraction. Addition and subtraction. Now, this is true when n is not equal to -1. If n is equal to -1, then you have natural log of x. So let's just try to find this. Let's show that this is true. And I'm just going to show it by taking the derivative of this to see if it will return here. So if y is equal to natural log of x, then let's find the derivative. That means derivative with respect to x of natural log of x will, never mind, that's not how I want to do it. So we want to find the derivative of y, which will be the derivative of this portion, right? Natural log of x. The best way to do this is not to have the equation in this form. You can, you can manipulate your function for convenience, and that's the benefit of algebra. You can do some manipulation to have it in a form that you recognize that makes sense to you, and then you convert it back to do some evaluations to go back to where you need to be. I wouldn't do it this way because I don't want to just put the answer there, right? What I would do is raise both sides to e. Now I have e to the y is equal to e cancels natural log x. Now I can take the derivative of both sides. So derivative of this side with respect to x is derivative of this side with respect to x. Now derivative of e to the y is e to the y. So we have e to the y, but when you're taking the derivative of a function in a variable different from the variable you're using to differentiate, then the variable over the variable of differentiation has to be written. So we have the y, the x here. And when we take the derivative of x with respect to x, we just get 1 because it's going to be dx, right? Now I can make this subject because I want to find the original problem question is y is equal to natural log of x, find what? dy dx, right? That's what we're trying to do. So I can just divide both sides by e to the y. So I have 1 e to the y, right? From law of indices, you have dy dx is equal to e negative y. Now, recollect that this is what? Y. Natural log of x is y. So I can update this and I'll have e minus natural log of x. Now, law of logarithm states that if you have some coefficient multiplying the natural log of any variable or number, you can move the coefficient in as an exponent. So this becomes e natural log of x negative 1. And this cancels this, right? So you end up with 1 over x. Do you see that? Or I would rather write it in this form, so x negative 1. So we can see that the derivative of ddx of natural log of x is equal to this. That means the integral of both sides, this will cancel out. So the integral of x negative 1 is df, or the integral of x negative 1 is natural log of x. Now, whenever you do indefinite integral, that means you don't have lower and upper limit, you have plus c, constant of integration. I didn't just add it there. But we can see that this, whenever the exponent here is minus, then you get minus 1, you have natural log of x. Now, I would like to interest us with the use of this identity up here before I get in here with U-substitution. Most often, you don't get the function as simple as this, or you don't have it term by term, polynomial looking real nice kind of setting. You might have a more complicated question. What you need to be looking out for is what else makes up the question. And I'll give an example. Say you have, think of a good example. You have x to the third, x to the second dx. This is just a simple example. It's easy to do this because I'll just expand this and I'll have what? X to the fifth dx, right? As simple as that, right? So integral is not distributive over multiplication. So whenever you do this, x third dx multiplied by x second dx. You cannot do that. Never make that mistake. You can only do that when it's plus or minus. Weak signs, if you have multiplication or division, you cannot do that. So back to what I was trying to demonstrate, because I just want to show you the power of what? Of using this identity with, U-substitution. And we can spend all day doing this, and you appreciate just this. What I realize is that you don't need to know too much. You don't need to know a lot in integral calculus to be able to do a lot. I do most of my integration by relating it to something simple that I know, and that's what I'm trying to teach. X squared dx, right? It's easy. Like I said, you have x to the fifth dx, right? And based on this, the exponent is what? 5. The exponent is 5, so you just have the solution as this, right? It's going to be x, the exponent n is 5 plus 1, and then you divide by the new exponent, which is 5 plus 1, plus c. Always add a constant of integration, because there are family of solutions, there are family of functions that you differentiate, and we'll give you this. It's not unique, and that's why we always add a c. This will give me what? X to the 6th over 6 plus c, right? Very easy. It is not always you can do that. Now, if I'm going to use U-substitution, let's assume I don't know what I'm doing. I know, so if I had called x to the third u, I can easily find the u dx, which is 3x squared. The derivative of this substitution has the function it is multiplying. That's what you always want to look out for. When you have some function multiplying some other function, the derivative of one of the functions gives the other function. When you have that, you can use U-substitution, after which most likely you will be able to use this. So what does that mean? I can find dx, because I have dx here. I can cross multiply. It implies that du is equal to 3x squared dx. Do you notice something? I have this, x squared dx, x squared dx. So I can divide both sides by 3, right? Divide both sides by 3. Do you see that? And what do I have? I have du over 3 is equal to x squared dx. I can replace the whole of x squared dx with this. So this integration, all this will go, because it's going to be u, right? U, and U substitution. X squared dx is the same thing as what? du over 3. Very simple. Why I'm showing this is because it's not essentially important to use that or advantageous to use that here, because this is straightforward. Just expand it, right, and do this one step or two steps. Or you get to see more complicated functions multiply each other, and then you have to use this. Now, this will be equal to 1 over 3 can go out, and we have u du. U du is u to the power of 1. So we're still going to use this. The exponent is 1, so we add 1, right? So we have 1 over 3, u 1 plus 1 over 1 plus 1 plus c. So this is going to be 1 over 3 times 2, which is 6u squared plus c. And you can now put back your substitution in the solution, so you have 1 over 6 x third squared plus c. And x third times third squared is x to the 6th. So this is 1 over 6 x to the 6th plus the same solution, the same result. And you will ask, why do I bother doing this? This is why. I'll show you why now. And we're just considering really simple cases. Let's assume you have integral x to the third plus 2x squared to the power of 20 multiplied by 3x. I want to make it attractive. So let me make this third. 3x squared plus 2x. Now, I'm just giving you an example because I know what it is, right? I'm just formulating something that will work out so perfectly. And a lot of questions are like that. They work out perfectly. Let me see. So, assuming this is 6, so this is 2. I hope it works out. But if you have something like this, you cannot expand this. How do you expand this? This is x third plus 3x squared to the 20. This is x third plus 3x squared, another x squared third plus 3x squared, 20 times. How do you want to expand that? This is the reason why U-substitution is so powerful. It is so powerful. Now, what do? Hopefully, the derivative of this gives me this. Hopefully. So let's try. U is equal to x to the third plus 3x squared. Let's see. So we have the u, the x is what? 3x squared plus 6x, right? It's not exactly, but what can we do to make it look more like, right? We have 3 into what? X squared plus 2x. Can you see this? This is what I want to arrive at. So we have du is what? 3x squared plus 2x dx. I just cross multiply. Now I can divide both sides by 3. Now what do you notice? All this is all this. So I can replace all this with du over 3. Can you see? And I can replace all this with u. What that means is that I will have integral u to the 20. All this is the same thing as what? Du over 3. So I can rewrite this as 1 over 3 integral u to the 20 du, and same thing. It doesn't matter because I use x here, and I have u here, u here. It's still the same. You use different variables, but the theorem or the identity still work. It doesn't matter what the identity, they are just dummy identity. It doesn't matter what you use. So now, I mean, variable you use, that's what I intended to say. So this would be U20 plus 1 over 20 plus 1 plus C. Now, I can just write it here. This will be what? 1 over 3 times 21 multiplied by 21, and then U to the 21 plus C. And what do you end up with? 1 over 3 multiplied by 21, and then you can now substitute back what your 21. You cannot survive multiplying this, expanding this out, but with U-substitution, we are able to do it. Now, can you see how lengthy, not so lengthy though, compared to expanding it out and trying to solve it? But I'm sure you don't want to always do this, right? I don't. Yeah, at least I don't want to do this. So, there is an extension of this identity. And the extension of this identity I'm going to write up here, and then I'll solve this question again. So if I have integral f of x to the n f prime of x dx, then this gives me integral, the integral of this gives me f of x n plus 1 over n plus 1 plus c. I don't want to write the plus c, we know we'll put plus c, and natural log of f of x if n is not equal to minus 1 and if n is equal to minus 1. Is an extension of this. This is a summary of U-substitution. Let's solve that question we just solved again. We have integral x to the third plus 3x squared to the 20 multiplied by x to the second plus 2x 2x dx. Find the derivative of this. This says if the derivative of this multiplies all this. If two functions are multiplied by each other and you want the integral, if one of the function, the one without the exponent, is the derivative of the one with the exponent, then the result is this if n is not equal to 1, of course not 0 either, and equal to this if n is equal to negative 1. So let's find the derivative of this. The derivative of this, if f of x, so f of x is equal to x cubed plus 3x squared. So what's f prime? X cubed plus 3x squared. So what's f prime? F prime is 3x squared plus 6x. Is it this? No. But in maths, you can do manipulations that help you arrive at your destination as long as it doesn't change the question. What I mean is that I can multiply this by 1. What I mean is that 1 is the same thing as 3 over 3, right? Divided by 3. I know that if I multiply this by 3, 3 over 3 is 1. I've not changed the question, right? 1 times this integral is the same, right? If I move this 3 in, right? If I move this 3 in, I'm gonna have 1 here, 3 here, and 6 here. What have I done? Now this derivative of this, the derivative of this is this, right? So 1/3, I've been able to manipulate it without changing the question, because if I factor the 3 out, it will go away and I have my original question. But now the derivative of this is exactly this by this check. So instead of writing everything, since the derivative of this is this, I'll just write the 1/3, write this, x to the third, 3x squared, and add 1 to the power, 20 plus 1, and divide by 20 plus 1. And this will be 1/3 multiplied by 21, x to the third, 3x squared, 21 plus c. Beautiful, right? Makes life easy. So this is also an identity. It is an extension. Extension of this. An extension of this. Let's try it for something that has natural log. Okay. So I'm going to wipe this off, but I'll leave that up at the top. So again, if you have the same question, I don't need to use the same question, but if you have integral something like this. Or x to the power 2x squared. Something like this. I can rewrite this as 2x squared plus 1 negative 1 times x dx. All I need to check, it looks like this. It looks like this with an exponent negative 1. So let's find the derivative of this. F of x is equal to 2x squared plus 1. So f prime is 4x. The derivative of this is 4x, but we don't have 4x here. Same way, I can multiply by 1, which is 4/4, because I want to have 4x here. I can move this in here. Now, I've not changed the problem because I multiplied by 1. Now, the derivative of this is this. The exponent is what? Negative 1. So it should follow this. That means since the derivative of this gives this now, whatever is outside, you still have to write it. It is just going to be natural log of that function. 2x squared plus 1. Straight up. You don't need to say let u be this, find the u, the x, and then substitute it back. You just skip all that and just apply it. Power of U-substitution. And this is just one of the several examples where it is evidence that you can do this kind of substitution. Oh, sorry, I didn't mean to wipe this off. I want this to stay. F of x to the n f of x y, and that is equal to this. Yeah. Now, we'll still visit this with more examples and show how to use this. I'm just going to introduce this. Now, sometimes you have this is integration by part. Sometimes you have you need to evaluate the integral of the product of two functions that are so different, not related in any way. Sometimes integration by part is the way to go. How do you know when integration by part can work for a question? If you have two functions, let's call it f of x, g of x. How do you know if you can use this? The question you ask yourself is one of the two functions differentiable? Can you find the derivative of one of them? If yes, the product of that derivative and the integral of the other one, is it integratable? Let me explain it again. If you have the product of two functions, it is easy to differentiate one and it's easy to integrate the other, but it's not easy to integrate both when they multiply each other. Then you probably can use integration by part. Another way to see if you can use integration by part is if the part of the function that you can differentiate drops out when you differentiate it. And then the other part is easy to integrate without the first part, or the part that could differentiate. You could differentiate. That is also a way to know. I'll give an example. Let us assume you want to integrate x e to the x. And I know I've not done anything with exponential, but one thing you know is that the integral of e to the x is e to the x. It doesn't change. That's why it's okay to use this, because I'm not really introducing anything new that much. I don't know how I could evaluate this product, and I cannot use U-substitution, because if I take the derivative of this, I don't get this. Likewise, if I take the derivative of this, I don't get this. So this cannot work. But I know that if I don't have this guy there, I can integrate this. But my problem is when I have the product, I cannot integrate. So if I differentiate this, the derivative of x is what? 1. Then I'll be left with this. So what it means is that this can work for this question. Now, we want this to be differentiated. So we call this u. The function you want to differentiate is what you call u. The function you want to integrate is what you call dv. So we just need to find uv and substitute in there. uv du, right? Now we have that my u is x. It implies that my du is 1. I'm just finding everything that I need to substitute. My dv is e to the x. It implies my v is e to the x. So this one is u. You differentiate it to get du. dv is this. You integrate both sides to get v. Now the integral of e to the x is e to the x. That makes it easy. So we have everything we need to substitute here, right? So now we're going to have u. We're going to have this integral, x e to the x will give me u, which is x, v, which is e to the x, minus integral v e to the x du is 1. So times 1. So this will give me x e to the x, integral of e to the x is itself e to the x. Of course, plus c. You see that works out perfectly when you have two dissimilar functions. They are not similar in any way. The derivative of one cannot give the other. You most likely will be able to use U-substitution. Sorry, integration by part, if at all it is an integration that is an integral that is possible, that can be done. I will give another example to make it clearer. Let's say we want to integrate x sine x dx. The derivative of this is cosine. The integral of this is negative cosine. The derivative of this is 1. The integral of this is x squared minus 1. They are very different. No similarity between them. But I know that if I differentiate this, it drops out and I will be able to integrate this. So same thing, we can use uv minus integral of v du. So we just need to determine what u is and what dv. If we differentiate this, it goes away. So I want it to be my u. My u. And if I integrate this, well, I can integrate this, so this is my dv. So now I just need to find everything I need. U is x. It implies that du is 1. dv is sine x. It implies that v is minus cosine x. And how to check this is derivative of cosine x is minus sine x. So integral of both sides, this will cancel this. Integral of minus sine x is equal to cosine x. So I just multiply both sides by negative. And I will give trig identities later. So we'll be clear with all that later. So now I'll just substitute in here. So x sine x integral will be uv. U is x, v is what? Negative cosine x, minus v is negative cosine x, the u is 1. Now, negative x cosine x minus minus will give me plus integral cosine x. Derivative of sine x gives me cosine x, so integral of cosine x will give me sine x. So this will give me minus x cosine x plus sine x plus c. Very dissimilar, but it is easy to integrate that using by part. And that takes me back to something I won't talk about that until I do trigonometry and then use U-substitution again. Because U-substitution can be used in all identities. And that's why I like to show the usage, the power in U-substitution in any identity I discuss. I was going to introduce the U-substitution in trig, but no, I'll wait until this is done. Integral, trig integral identities is done before I do that. Now, one thing you should note, sometimes you might need to use integration by part more than one time, several times, to solve a question. And I think it's called reduction method, but it's still essentially integration by part, cascaded, repeatedly done on a piece of question. I will give an example of that. So say we have x squared sine x instead. Now they are still they're not similar, and I don't know what to do here. But I know if I differentiate this, it drops down to 2x. And when it's x, I can differentiate it again. I will call this I. So I is uv minus v integral v du, right? Now I want this to go away. And when I differentiate this the first time, the power drops down. I differentiate it the second time, the power, it becomes a constant. So it's easy to see that this is my u and this is my dv. So we're going to use that to find du, sorry, let me write it. U is x squared, implies that du is 2x, right? And dv is sine x, implies that v is minus cosine x, right? Now, I called it I because I don't want to keep writing it. It's easy. I want to find this integral, so I call it I. So I have I is equal to what? uv. 2x, which is, x squared, which is u, v minus cosine x, right? Minus v minus cosine x minus integral v du, right? Du is 2x. This I can update and have I is equal to minus x squared cosine x plus integral, I can bring the 2 out, right? X cosine x. Minus minus gave me positive, right? Now, I will do the same thing again. This portion, right? This portion can be solved using uv minus v du again. Now, this again will be my u and this will be my dv. So if u is x, it implies that my du is 1, and if dv is cosine x, my v is sine x. Because when you differentiate sine x, you get cosine x. When you integrate cosine x, you get sine x. So this portion can be expanded as this, right? So that means my I will be minus x squared cosine x plus 2 into the integral of this, which is uv. U is x, v is sine x, minus integral v, which is sine x du. And you see, what is left is just this. It's easy to integrate, right? So we have I is equal to minus x squared cosine x plus 2x sine x. The integral of sine x is negative cosine x, because the derivative of cosine x is negative sine x. Or the derivative, or sorry, the integral of negative sine x is cosine x, right? So I'll have plus 2 cosine x. I have 2 because these 2 distribute in, but the integral of this, integral of sine, will give me negative cosine. Negative, negative gave me positive here. And then I can have plus c. So sometimes you need to do it several times to solve the question. I'll give 2 more examples using integration by part, where you have to do it a couple of times. One you have to do a couple of times, and the other one is just tricky, and I would like to give that. And then I'll probably stop for this video, and then I would have integral, trig integral identities in another video. So I can leave this here and do it there. Let me change. Oh, no, it's fine. Now, what if I have this question? This one is interesting because it is interesting. I mean, because you have to do it 2 times or so. I think it's 2 times, and then you get what you wanted. The original question will reappear. So let's assume you want to find the integral of this. In this case, it's easy to integrate this on its own. It's easy to integrate this on its own. It's easy to differentiate this. It's easy to differentiate this when they are on their own. So you can choose anything. First of all, let's call this I. You can choose anything as your u, and you can choose anything as your dv. uv minus v integral v du, right? So I'm just going to pick any, it doesn't matter, dv, right? I'll show you what the key is. I've made that mistake before, and that's why I'm going to emphasize this. Okay. If my u is e to the x, it implies that du is the same e to the x, because the derivative of e to the x is e to the x, integral of e to the x is e to the x. Since my dv is sine x, it implies that my v is, by integrating this, is minus cosine x, right? Because if I differentiate this, I'll have minus sine x, minus minus gives me plus, right? I like to check. Now, my I, which is the integral of this function, will be uv minus ex cosine x, because u times v, I just put the minus in front of the product, minus integral v, which is minus, so minus cosine x du e to the x. Now, I'm going to rearrange this. Minus can come out and multiply this minus. So I can write it as plus, right? Plus, but I'll write the e to the x first, cosine x. Are you good? Now we're going to use the same integration by part here again. And yes, here, this is where most people make mistake. What did you take as your u? E to the x. You have to maintain the same u. In this question, it is coincidence that it did not change, right? You have to maintain the same u. So if your initial u resulted into a different function here, you have to call that new function that resulted from the initial u again. If you call this dv and you call this u, you're going to reverse the process. What it means is that since this was dv and it gave rise to this, it resulted into this. This again has to be dv, and this must remain u. So our second u will be e to the x. It implies that the u is e to the x, right? My dv is cosine x, implies that v is sine x. Now I will continue by solving this portion, uv plus integral v du. So this portion is going to give me this again, but using this, right? So I have I is equal to negative e to the x cosine x plus, I'm just going to put everything in bracket because I'm expanding this portion, right? uv, this times this, so e to the x sine x, sorry, this is minus, my bad, minus integral v, which is sine x du e to the x. I will continue up here. Now, I is equal to negative e to the x cosine x. I'm going to expand this, plus e to the x sine x minus integral e to the x. I'm just rearranging sine x. Now this is where you have to factor. I is e to x sine x. E to the x sine x. That's what we want to evaluate, right? Look at it. It reappeared here. So we have I is equal to negative e to the x cosine x plus e to the x sine x minus I. So now you can factor it. So you have to know when to stop, when it shows up again in your integration on your right hand side. That's where you stop, when the original question integral shows up on your right hand side. You stop there. So this is negative e to the x cosine x plus e to the x sine x. So I can divide both sides by 2. So I is equal to, I can factor e to the x out over 2 minus cosine x plus sine x. And I can add a constant of integration. Therefore, my I my integral e to the x sine x is e to the x over 2 negative cosine x plus sine x plus c. Now, that's how you do it. One last question I will be solving, and I'll solve it here because it's interesting. It's a question that always caught the interest of people, at least me, is this. And I'm going to solve it here so I don't have to wipe that. Using integration by part to find the integral of natural log of x. I don't know how to do this without integration by part. It's not a known identity that I can relate to something else. And I cannot use this identity either. But I can multiply it by 1. It is hard to differentiate this. Sorry, it is easy to differentiate this, but the problem is integrating it. But it is easy to integrate this, right? And when you differentiate this, so if I call this dv, dv is natural log of x, it implies that what? V is, oh sorry, I said the right thing, did the wrong thing. It is hard to integrate, so I'm going to call it u. So if this is u, natural log of x, it implies that du is 1 over x. Derivative of this is x to the negative 1. So I took the derivative and I got 1 over x, right? And if this is the v is 1, it implies that v is x, right? So we're going to use uv minus integral v du. Now, the result of v and du is easy to integrate, and that's the key. So integral lim x is equal to dx equal to uv. U is this, v is this, so x lim x minus integral v x du 1 over x. You see? That's the key. This gives us x lim x minus integral 1. X for sure. And this integral of a constant or 1 is x. I just thought this is an interesting question, and that's why integration or integral, and that's why I added it. Now, I wouldn't be able to cover trig integral identities here because it's still this video. I don't want it to be too long, but I'll make subsequent video. It's not gonna be one video to come. I'll make several other videos because while I thought I'm gonna make just one video in integral identities, but I realize it's a lot and it's good to show all those extensions, identity extensions, because it is helpful to see them. Thanks for watching, and stay tuned for my next video.